All right, good evening. My name is Hunter, and this is content review for general chemistry students. Today we're going over acid-base titrations. Um, if you can hang for this unit, the rest of your equilibrium stuff that you'll encounter in the future will be easy by comparison. Um, this is a little bit challenging, but it's worth it to kind of understand um, some of the logic behind these processes and get a lot of practice doing them. So I will be the first to admit that I had to do some study to be ready for today's live stream, and I found that a lot of the stuff online was um, more than was needed, and kind of obscured the lesson a little bit. And it was very helpful for me to go back to my notes from Dr. Paletti's class because it gives you a couple shortcuts that you can make with making reasonable assumptions. So last week we talked about buffer systems and the conjugate acids and conjugate bases uh, being the system of interest, and titrations are very much the same thing, but it's allowing us to determine unknowns in solutions, which is kind of cool. So I've also used these kinds of calculations for my job, making soap, because you're dealing with strong acids or excuse me, strong bases, and that can get pretty exciting if you have too much or too little. So this example, this first one is in your OpenStax textbook. They even give you the answers, but you do have to work through them yourself. So that is what we're going to do, and we'll be able to check our answers against the answer key in the book, which I neglected to include here, but that doesn't matter. All right, so we're calculating the pH of the weak acid and strong base titration between 50 milliliters of zero point 0.1 molar formic acid and 0.2 molar sodium hydroxide. This is our titrant at the listed volumes of acid and bases. And the first one that we're doing is 0 milliliters of titrant. And what this tells us is that we're first solving for our initial point. First, though, I think it's worthwhile to kind of look at the dissolution of formic acid, which is aqueous. You will see weak acids notated as HA. This is in equilibrium. It loses a proton, which is aqueous. And then we have formate, which is our conjugate base. So again, this can be notated H plus, and this will be A minus for these purposes. So A minus is the conjugate base to our acid, HA. You will also see AHA if I read this backwards. And this is a mnemonic that will come in handy a little bit later. Some other important stuff that we need to remember. Actually, yeah, this AHA mnemonic is helpful for remembering the order for your Henderson-Hasselbalch equation. And that's pH equals pKa plus the log AHA, concentration of conjugate base over the acid. That'll come in handy in a minute. There's some other information that we need before we can really start answering these questions. So for formic acid, we need to look up the Ka value. This is the ionization constant for formic acid. This is just a tabulated value. You have to look it up. It's 1.8 times 10 to the negative 4. Now, from this value, we can determine a lot of other important values. This should be review. We have pKa equals negative log Ka. So that'll be negative log 1.8 times 10 to the negative 4. Plug that into your calculator, and you should get 3.74. That is your pKa. Now formate, which is our conjugate base to formic acid, we can determine its Kb value. This won't be immediately important, but it will be in a bit. And that's Kw, ionization constant for water, which is 10 to the negative 14, divided by the Ka value, which is 1.8 times 10 to the negative 4, gives you 5.6 times 10 to the negative 11. This is all preamble. This is just so that we can start solving these equations. So when you're confronted with these, it may or may not be important to do this work on the front end. It'll make all of this a lot easier to do. And then we have initial moles of our acid, of formic acid. We're given that there's 50 milliliters and we're given a concentration. So let's do a little dimensional analysis. We have, yeah, 50 milliliters. Our molarity is given in moles per liter, 0.1 moles per 1,000 milliliters. Is my mic still working okay? Yeah, monitor seems to think so. So 50 times 0.1 divided by 1,000 gives us 0.005. This is moles of formic acid, of our acid of interest. Now we can start solving these problems. So I'll be referring back to that a lot. Our first one, we're solving for 0, adding 0 milliliters of sodium hydroxide. In other words, what is our initial point? There's a reasonable shortcut that we can take here. And this is based on the Rice tables that we did previously. Our concentration of hydrogen ions, the proton that the acid is donating, is equal to the square root of the Ka value times the initial concentration of acid. The proton concentration is what's interesting to us because that allows us to get to the pH, right, which is what we're solving for. So proton concentration equals, our Ka value was 1.8 times 10 to the negative 4 times our initial concentration, and that was 0.1 molar. Gives us 0.00424. Now we can solve for pH. pH equals the negative log of H keep this in the same column, equals negative log 0.00424 equals 2.37. We can check our answer key and that should be the answer. So this is very, very acidic to begin with, right? And now as we do our titration, as we add our first 15 milliliters of sodium hydroxide, we're going to make that more basic. We're really going to be creating a buffer solution where we have our acid plus hydroxide. We're not worried about the sodium, it's just a spectator ion. And this will be in equilibrium with H2O. Hydroxide takes that proton off of the acid, and our conjugate base left over. So since we have this acid and conjugate base combo, use the Henderson-Hasselbalch equation. All right. That equation, Henderson-Hasselbalch equation, is pH equals the pKa plus the log of conjugate base over acid. And to get there, we need to do a little bit more math. So this is a chart that really helped me. We have initial moles of our acid. And have we already solved for that? We did. Initial moles of acid, we had 0.005 moles. We're going to do that as scientific notation. 5 times 10 to the negative 3 minus the initial moles of hydroxide. So we're given 15 milliliters. We have a little bit of math to do. That's 0.015 liters of hydroxide times, it was 0.2 molar per liter, and that gives us 0.003 moles of hydroxide. So that's here. 3 times 10 to the negative 3. Same thing, just in scientific notation. Subtracting 3 from 5 rather, gives us 2 times 10 to the negative 3. And this is our current moles of acid that will be left over after the hydroxide reacts with the acid. All of the hydroxide is reacting to completion because it is a strong base. And so we're not going to have any hydroxide left, but we are going to have this conjugate base. And that is the same as the concentration of hydroxide that was that dissociated. So that's 3.0 times 10 to the negative 3. Okay, so now we have all the information that we need to finish solving our Henderson-Hasselbalch equation. Our pKa value, we solved above, right? Yes, it's 3.74. Plus the log of conjugate base was 3 times 10 to the negative 3 over the acid that's left over, and that's 2 times 10 to the negative 3. And that should give us 3.74 plus. Sorry about my dog in the background. She's been very preoccupied with the neighbors next door. 3.916, and we should be done. So after adding 15 milliliters of sodium hydroxide titrant to our acid, we now have a solution that is slightly less acidic. Still pretty intense though. Just giving myself a little bit more room to work with. All right. So now we're doing 25. So we got to figure out how many moles we have. But we're going to follow a very, very similar process. It's 0.2 molar gives us 0.005 moles of hydroxide. This should be ringing some alarm bells because we said that our initial concentration, or rather our initial number of moles for the acid was also 0.005 moles. And that's important because this tells us that this is the equivalence point. The point at which all of the initial acid will be consumed by the titrant species. So here we get to make some reasonable assumptions based on that, and we get another shortcut. And we get to use not the same, but a related equation to the one that we did up above. And this is based on, if you remember our rice tables from last week. Now we're going to be using the Kb, the ionization constant for our base, times the initial concentration of conjugate base. So be careful. This concentration, we also need to figure out what our new volume is. So we started with 50 milliliters of solution. We're adding 25, gives us 75 total milliliters. We know that we're going to have 0.005 moles of our conjugate base because all of that acid is reacting with hydroxide. Divide that by our new volume, the total volume, and this gives us our concentration, which is 0.066 repeating. So that's the concentration of our conjugate base. Our Kb value for that conjugate base for formate, we calculated earlier. And I just got a low battery notification on my headphones. So give me just a second to switch over. Okay, unfortunately, this also means that I had to switch microphones, which is going to change the audio quality. I apologize. Okay. That should help a little bit. Where were we? Our Kb value, which we bothered to calculate on the front end, because it's going to save us a little bit of work here. So that Kb value for formate, which is our conjugate base, was 5.6 times 10 to the 11. The initial concentration, the concentration that we have of that conjugate base, we just calculated, which gives us our concentration of hydroxide at 1.9326, giving myself some extra sig figs there, times 10 to the negative 6. This lets us determine our POH, right? Equals negative log times that concentration of hydroxide, 1.93 times 10 to the negative 6, gives us 5.71. We're not done yet.
pH equals 14 minus POH equals 8.286. And now our solution is basic. So at the equivalence point, where all of the hydroxide has consumed or reacted with the acid, we have a basic solution. And this makes sense, right? A weak acid is going to have a, by comparison, much stronger conjugate base. Strong acids and bases have weak conjugates by comparison. Boy, I'm really just taking up all the space. Okay. So that was our equivalence point. Now we're just going ham, and we're going to add an excess of sodium hydroxide. We've got 0.03 liters. That's 2 molar, 1 liter. The other way you could have gotten here, we already calculated 15, what 15 milliliters has, and that is double the number that we calculated previously. So if you need additional shortcuts, save yourself a little bit of time on like a timed exam, for example, you can do that. So we double the volume, double the number of moles. Okay, this one, the logic is a little bit inverted. We know that we have an excess of sodium hydroxide because we have already determined what the equivalence point was. So we can take an additional shortcut here, and using a similar table to the one that we had previously, we had current moles of hydroxide. That's 6 times 10 to the negative 3 minus the initial moles of acid, which we had previously calculated. Come on. Right, because we're not going to have any acid left over, but we are going to have some hydroxide in excess. Six minus 5 is 1, times 10 to the negative 3 moles of hydroxide. The other thing that we need to know is the current total volume of the solution. We started with 50 milliliters, 0.05 liters. We added 30 milliliters, 0.03 liters. Gives us 80 milliliters, 0.08 liters. And now we simply take moles divided by liters, which gives us our new molarity, which is 0.0125 moles per liter in hydroxide. All right. Now we can solve for pH. Our POH is the negative log of that concentration. So negative log 0.0125. That equals 1.903. pH is 14 minus that number, 12.097. Extremely basic. Which makes sense, because sodium hydroxide, being a strong base, will have a much greater impact on the pH of this solution than will the weak acid that we started with. Okay. So we're about halfway into the stream, which is great. Um, Now we have a bespoke problem given to us by Dr. Shagley here. So we're given 90 milliliters of a 0.6 molar solution of the weak base ammonia. And he was nice enough to give us a Kb value here, which is great. And a 1 molar solution of the strong acid titrant hydrogen chloride. What is... Well, before we even get started, let's remember some of those things that we needed to get started here. So now we're doing a weak base. So we'll note this B with a strong acid, which is a source of protons. And this is going to form our conjugate acid, which we'll notate as BH+. Okay. We're given a Kb value, thanks, 1.8 times 10 to the negative fifth. So our pKb then is simply a negative log of that, so we've got 4.74. pKa is 14 minus the pKb equals 9.26. So working backwards from pKa, it's simply 10 raised to the negative pKa. So 10 to the negative 9.26 equals 5.6 times 10 to the negative 10. Okay. I think that's everything that we're going to need for this set of problems. So for the first one, what is the pH before any acid is added? This is just asking for our initial point, but we're dealing with a base. Well, yeah. We're dealing with a base, so we're going to have ammonia reacting with water to form hydroxide ions. And we're going to use that shortcut again, Kb times the initial concentration of base. And, what is our initial concentration of our base? That would be, let's do it over here. We had 90 milliliters of base at 0.6 moles per liter. Gives us 0.054 moles of base. Okay, so that's our initial. Move that over there. Equals Kb times initial. Should get 9.859 times 10 to the negative 4. Very, very small quantity. POH equals the negative log of that. Gives us 3.006. 14 minus that number gives us the pH. And as expected, our initial point is basic, as it should be. It's important for me to go back and make sure that my answers make sense given the prompt. Save me from some really silly mistakes. So question B, what volume of acid in milliliters is needed to reach the equivalence point? So we talked about what the equivalence point meant before. In this case, we're adding strong acid. So all of our acid is going to dissociate. Our quantity of acid needs to be equivalent to the amount of base that we started with. So we had our initial quantity of base. Let's point at 0.054 moles of ammonia. Because we're working with 1 molar strong acid, it's 1 mole per liter, it's pretty easy. I mean, I'll do it. Sorry. Dimensional analysis. Moles go on the bottom. Per 1 liter. It's just times 1, which means that it's equivalent. So our quantity of strong acid is, I'll go ahead and show the dimensional analysis just to So we need to add 54 milliliters of strong acid to get to our equivalence point for this particular titration. C is what volume of acid in milliliters is needed to reach the halfway point where pH equals pKa. Okay, so this is kind of cool. That's just a good factoid to have memorized. That is something that certain standardized tests love to check your knowledge on. They love using that question as a way of finding out if you understand titrations and the various equivalence points. So pH equals pKa at the half equivalence point. Let me make sure that's actually, yeah. So here again, our pKa was 9.26. So that's where we're shooting for. So we had our initial moles of base. And the reason I'm bringing this back up is because where at the equivalence point all of the base was getting consumed, here half of it is being consumed. So we're going to have an equal amount. Sorry, that's 0.27. We're going to have equal amounts of our base, ammonia, and its conjugate. And that is what this half equivalence point means. Half of the base has been consumed, and half of it exists as its conjugate. So 0.027 protons are needed, moles of protons. We have our 1 moles per liter solution. So 0.027 liters of HCl are needed. times 1,000 for milliliters gives us 27 mLs of HCl. Okay. For the next one, we were asked to do 50 mLs of HCl. So this is going to be, if we set the equivalence point, let me think here for a second. So 54 milliliters would get us to the equivalence point. So this is still going to be in the buffer range. So we have a little more work to do. We're going to use that chart again. We had that initial moles of base, and we're adding protons. Our initial was 0.54, and we're currently adding 0.05 because it's a 1 molar solution. The volume is equivalent to the number of moles, which makes it really easy. So moles of base minus moles of a strong acid gives us 0.004, and that's current moles of base left over. And we're going to have current moles of conjugate. And that is all of this. Okay. What am I forgetting here? No, I think we're good. We can use this Henderson-Hasselbalch equation. We just need to be careful again. This is where having the complete form is really helpful. So for the weak acid with a strong base titration, it was AHA. All you have to remember here is that the conjugate, the one with the proton, is on the denominator. So before, we had our conjugate base over acid. All you really need to track is that proton being on the bottom, if that helps you memorize it. Okay. We've got our Henderson-Hasselbalch equation. We already figured out the pKa we already figured out our pKa was 9.26. We have our remaining concentration of base and our new concentration of conjugate. Number of moles, rather. Yeah. Hit that through the calculator. We get a negative number, so just be careful with that. That's a 9. So pH equals 1.137. Excuse me, I'm looking at the wrong thing. 8.16. That makes more sense. So still basic, right? Value greater than 7, which would be neutral. Okay. CD, we've got E. E is asking for the pH at the equivalence point, which we already calculated. So we can again use that shortcut. And that was Ka plus the concentration of, we're interested in the conjugate acid in this case, since we started with a base. So we need to be careful here. This number includes the total volume that we have after adding our titrant. So we started with so at our equivalence point, we added 27 milliliters. Of HCl. We started with 90 milliliters. So our new total is 0.117 liters. Our Ka value we calculated above was 5.6 times 10 to the negative 10 times this new concentration of conjugate acid. All told is 1.137 times 10 to the negative fifth. That's our concentration of protons. pH equals the negative log of that number. Gives us 4.94. Which is acidic, which makes sense because we have added enough strong acid to consume all of the weak base that we started with. All right, what's our last one here? What is the pH after 60 milliliters of acid is added? So now we're dealing with an excess. And here, same problem we did before with the weak acid and strong base calculation. So we have 0.06 times 1. Moles of HCl. We know that this is in excess, so we have current moles of, this is our source of protons, is 0.06 minus our initial moles of base was 0.054. Gives us excess moles, and we'll worry about that in a second. Is 06. And then we have our current total volume. Magic of computers is I can just move that over, which is nice. We have 0.06 plus, what did we start with? 0.9? 0.09? Yeah. 0.006 divided by 0.15 gives us our new concentration. We are 0.06 molar. And actually not HCl, we just care about the protons. Cool. Yeah. pH equals negative log times that number gives us 1.222, which should be our final answer. Very, very acidic, which makes sense. We've added an excess of a strong acid. It should be very acidic. And it is 4:46. That is our live stream. Hope you all enjoy your weekend. Good luck on your exams. Feel free to reach out if you have any questions, and I will see you next week.